About how she's a super mom.
I went to bed at 1.
And got up at 3?
No, got up at 6.
Oh.
But I was tired enough, I thought about canceling lab today. I was going to cancel lecture, but it worked out fine. It worked well. It doesn't always work, but it worked well. Back to Catherine in the morning class. Not Catherine,
Amy?
anyway. She said I am recording. I felt the same way. Because I wanted the first thing I did was I woke up and looked at my cell phone to see if it said this.
That's the same thing I did. I looked at I just had that
I thought about it. I really did. But I wanted to be done with this today.
Oh, no, not yet. So what are we doing? What's the order of classes?
So we're going to lecture for an hour. I'm going to lecture for an hour and 15 minutes. Muscle stretches and different types of muscle movements. We have a quiz and then we have the wet lab with the rapid stuff.
Like have a quick 30 minutes study.
Yeah.
Я не наша держит.
No, there's no particular title in here. Technically, probably yes.
No, 3 sugar-free caramel, 2 sugar-free caramel. I write it. Trish, what are you doing after class? Studying. What are you doing? Going home. Why? But I don't have my car. So I was going to see if you wanted to give me a ride. Well, I can figure it and just come back. I can walk a mile.
I know.
Yeah, we're going to stay and study and do that. If I didn't have to work, I'd stay and study.
You know what I have?
Depends on what time we get out.
Okay.
Because you will have.
Over here. Why are you sitting next to him with that?
He wants to go to the library.
I've never
He
seen
doesn't
you
even say hi to me unless it's on the other side of the room.
Nothing must have happened.
We put them off the table, it just got too small.
Between those two?
Yes.
Just stop beating.
Huh?
Just stop beating.
He didn't even hear me. It's all right. He's an abuser. Right. Yesterday, my class was like, well, I'm off the table. You should sit here. And I'm like, I need him to sit here and stop my pen from rolling off the table.
He knows how it's used.
He does.
Okay, Joe has a tender time.
I don't want to go there. That's the same concept of romance. All right. So today we're going to look at some generalized sort of concepts, not of the physiology inside a muscle cell, but of the tension created with a muscle cell pulling on a weight or a structure. And there's 2 ways of looking at this concept. One as an individual muscle cell and one as a muscle bundle, a group of muscle cells. All of the concepts of one muscle cell applies to multiple muscle cells except for one. So I'm going to keep reminding you whether we're talking about a single muscle cell or multiple muscle cells. Now, when I drew a line previously, when we were talking about a nerve, you interpreted this correctly as depolarization and repolarization, right? When you see something like this with muscle, it has nothing to do with electrical current. It has to do with a contraction and relaxation and increase in tension. So this is measured by, you would see this in the Physio Act, if we're using a whole muscle bundle, which is a little easier to do. A muscle such as the back of the leg, the gastrocnemius, in a frog is easy to get to. So the tendons are cut and suspended from a hook. The muscle is about 1.5 inches long. So this would be a muscle bundle. As I said, this is an experiment. It's easier to work with. and then a load is added, a weight is added. So a metal ball or box is hooked onto the end. So the muscle cell has to generate a force to shorten, okay, because gravity is pulling on that weight. And then an electrode is inserted into the muscle, and the stimulus is given via an electrical current. This can be done in a similar fashion under microscopic conditions with a single muscle cell, all right, but it's a little bit more difficult and not done in a student laboratory. So this is attached to a graph, so a pencil or pen on a rotating piece of paper on a graph. It's the old-fashioned way. Now it's done with computers. And so as the muscle shortens, pulling up on that weight, it will cause the needle or the recording pen to deflect upward, showing that there is an increase in the force created, pulling the weight up, and then as the muscle relaxes, the pen deflects downward. All right? So rather than showing an increase or decrease in the number of positive ions in the cell, this is showing an increase in tension or force created by the contraction of either a single muscle cell, a myofiber, or a whole muscle. All right? Now, a muscle twitch refers to the contraction of a single muscle cell. So I've drawn a muscle twitch here. If this is in reference to a myofiber. Now a muscle twitch can occur relatively rapidly. So here the shortest ones are anywhere from about 5 to 7 microseconds from beginning to end, right? And a long muscle twitch could be 40 to 100 microseconds. So towards the end of lecture today, we're going to talk about fast twitches and slow twitches. All right? So this would be a fast twitch. This would be a slow twitch. What do you think allows a muscle cell to have a quick contraction and relaxation period versus a slow, sustained contraction and relaxation period? Since it requires calcium for a muscle cell to relax, you might think it would be the rate at which the calcium is returned to the sarcoplasmic reticulum, but it's not. It's that myosin ATPase on the myosin head. Some are slow acting, take a little while longer to break down the ATP, and others are quick acting. The quicker the ATP is broken down and providing energy, the quicker the myosin head can return to its cocked position and rebind. If it's a slow-acting ATPase enzyme, it takes longer for the ATP to release the energy and for the head to return to its cocked position and bind to the actin myosin again. All right? So the quicker acting that myosin ATPase is, the quicker a muscle can contract and relax. And that provides our fast twitch and slow twitch type of muscle cell. Now, as we'll see at the end of lecture today, that also is part of the characteristics of the dark and the light meat that you see in the turkey that you may or may not be eating on Thanksgiving. In humans, we tend to have a variety. With one muscle is going to have maybe more of the fast twitch, but also some of the slow twitch. Okay? So we talk about generalized characteristics rather than the entire muscle bundle being all fast twitch or all slow twitch. But you probably know of individuals who are better at sprinting than long distance running. All right, so if they're better at sprinting than long distance running, they probably have more of the fast twitch muscle cells in their leg muscles. All right, if they're better at long distance running, they're going to have fewer of the fast twitch, maybe more of the slow, but we added another characteristics called oxidative or glycolytic, and again, I'll bring that back in. All right, so let's look at some images. Still talking about a single muscle cell. However, these images would apply to a whole fascicle or named muscle as long as they all have the same threshold. All right? As long as they have the same threshold potential, you would see a similar characteristic. So we're looking at these series of images here. So let's go through them slowly. So the line that I'm drawing, again, is not a resting membrane potential, but showing zero tension. All right, so this represents zero tension, a relaxed myofiber. Now we're going to provide a stimulus. The length of the arrow indicates the strength of the stimulus, translating to the number of acetylcholine molecules released binding to their receptors, translating to the number of sodium ions entering the cell and depolarizing it. All right? So if the stimulus is subthreshold, it will not reach the threshold potential of the voltage-gated channels in the sarcolemma around the motor end plate. Everybody with me so far? Remember, the motor end plate is that depression that the synaptic gluton fits into and has the ruffled edges where the ligand-gated channels are. All right? So we'll open some of those ligand-gated channels with acetylcholine because we get a stimulus, and some sodium ions will flow into the cell, but insufficient when they diffuse out to the surrounding sarcolemma to open the voltage-gated sodium and potassium channels. So we see no muscle response. All right? Nothing. Now, we can do this with the neuron, or experimentally we would do it with an electrode, but less than the sufficient current required, again, to open those voltage-gated channels. All right, so now let's do a stronger stimulus. There will be a latent period, or a lag time, and then we will see, let me draw that a little bit smaller, we will see contraction and relaxation. Okay. Now, we come back to relaxation again. I'm going to give a stronger stimulus, indicated by an even longer arrow. So now I'm above threshold. Maybe I have twice as many sodium ions flowing under the sarcolemma to reach threshold. What would you expect to happen? A stronger force of contraction or the same force of contraction? The same. Trick question, because I'm going to show you instances where it is stronger. Okay? So our all or none response says with everything else the same, even with a stronger force of contraction, all I'm doing is meeting the threshold of my voltage-gated channels. The same strength of current will flow in across the sarcolemma, down the transverse tubules, open voltage-gated, the same number of voltage-gated channels in the sarcoplasmic reticulum, and the same amount of calcium will open, bind to the same amount of troponin, exposing the same number of binding sites. So the tension is created by the myosin pulling on the actin. And if I have the same number of myosin heads pulling on the actin, I should get the same force of contraction. Okay? Hold on a second.
Is there a lag on that? Would there be a lag on that one?
Yeah, there should be a lag, sorry.
So that was my question.
Yeah,
There is a
there
lag.
should have been a lag. Okay? So this is illustrating the all or none response that we saw with a neuron is also present with the muscle cell. This looks like it's slightly higher. It's not supposed to be. Whatever. Look at the same height. Okay? Now, I'm going to take another muscle cell. May I erase this picture? Okay. I'm going to take another muscle cell. out of the refrigerator. Not really. I mean, I could, but what I mean is it's not been contracting and relaxing. Okay, it's fresh, it's unused, it's not been doing any kind of activity. So, a muscle fiber that is cold. I'm putting that in quotes, meaning it hasn't been exercising. It hasn't been going through a series of contraction and relaxation. All right? So let me give it a stimulus. I'm going to move this down just a little bit. Again, we're looking at a myofiber, a single muscle cell. Provide a stimulus that is of threshold potential. And I get a response. I get a contraction and relaxation. Just like I did before. Okay? I allow it to completely relax. And now I'm going to stimulate it again with the same force. I'm not increasing the strength of my stimulus. That stimulus is of the same force. Notice my contraction is creating a greater tension. I give it a stimulus of the same force again. Draw a straight line here. I get a contraction. Why is it, not why, but what's causing the greater force? It's still not the way I want to do it. I'm involving more myosin and actin, all right? So, but the difference, the reason for my single muscle cell is more myosin is binding to actin here, and even more myosin is binding to actin here. All right, that's why it's like adding another, I have my tug of war rope again, and I've got 10 people on each side here. And then I add 5 more people, and I add 5 more people. So the tension is greater, all right? Eventually, after a few stimuli of the same force, I'm going to reach maximum contractile force, and it won't increase anymore after that. Again, the stimulus is the same for each of these. This phenomena is known as TREP. If you look up on image search, and that's what, with the word TREP, you would see a bunch of images like this. You would also see several pictures of staircases, because that's what strep means. So this is also known as the staircase phenomenon. It appears to be breaking, an illustration of breaking the all or none response. Kind of, but my stimulus, I'm showing it different here. My stimulus should be the same. Okay? Stimulus strength is equal. Any idea what's going on? Why am I getting an increasing force of contraction with the same strength of stimulus? Notice again, I'm starting off with a cold cell. It hasn't been exercising. This is you getting out of bed. It's a couple of things. It's not quite calcium we're going to see with this, with the wave summation. All right, in tetany. This is because we're completely relaxed. The calcium is back in the sarcoplasmic reticulum. It's more the fact, a couple of things. Myosin I don't remember if I mentioned this in lecture. I did to the morning section. I don't remember if I did for you. But remember the axon is attached to the Z disc? Okay. Myosin is as well through a protein known as titin. Okay. It's kind of like a coiled protein. So as the muscle cell first starts to contract, that has to be stretched. Okay, so some of the energy involved is rather than pulling on the axon, it's getting this titin stretched. Some of it is stretching the collagen and elastic in the endomysium outside the muscle cell. A lot of it is the efficiency of the voltage-gated channels. Not all of them, and I don't know why, but not all of them appear to respond at first to the action potential coming down the transverse tubule. With multiple stimuli and exposure, eventually they're all responding. So our environment is not exactly the same each time. So that's kind of how we get around the appearance of breaking the all or none response. Our stimulus is the same, we're not increasing it, but we're just getting a more active, a more warmed up cell. That's why I said we have to start cold. So once the cell has been activated, maybe it has more capillary flow through, its channels, calcium voltage-gated channels are working efficiently, and then we get, finally at this point, with the same stimuli, the stronger stimuli, we're not going to see any greater reaction. So this warming up of a muscle cell, or of multiple muscle cells, because you can see this phenomena in a big muscle, as long as they're, because what's responding are all the cells that have the same threshold. So you would see the same phenomena with all the cells that had the threshold responding to this level. Okay, yes?
Would it happen that abruptly, like without any advances?
It might take about 5 or so to get it up, depending on the cell. The bigger muscle cell would probably take more.
Is that kind of like when you feel like stretching in the morning when you first
Yeah.
wake up?
Exactly what's,
Or just dynamic nervous with it?
yeah. Now, let's look at, so this isn't really shown on the screen. Let's look at that second diagram that's shown on the screen. Okay? So may I erase this image? So now we have, again, a single muscle cell or multiple muscle cells that have the same threshold. The cell is relaxed. This would be one that was warmed up, okay? It's past the trip response. We provide a stimulus. After the lag phase or late period, we get a contraction and a relaxation. We provide another stimulus of the same strength. We get a similar contraction. But now, after we start to relax, we repeat the stimulus, same strength. And the muscle cell responds by giving an even stronger contraction. This is known as wave summation. Same stimulus strength. First of all, there's a question in your mind that you should be forming by comparing what we see here with what we talked about with the neuron. What do you think that question should be?
The neuron had the absolute refractory period.
Excellent. Doesn't a muscle cell have, it has voltage-gated channels in the sarcolemma and in the transverse tubule and in our sarcoplasmic reticulum? So where is our absolute and relative refractory period? We're not using a stronger stimulus. All right. it does exist. A muscle cell does have an absolute refractory period. I'm going to draw in, but remember this is not electrical current that we're seeing here. This is the contraction and relaxation phase. Here is the action potential. By the time we give our second stimulus, the muscle cell is already past the relative refractory period. Our voltage-gated channels are capable of responding again. So the action potential of a skeletal muscle cell lasts much shorter than it lasts about 2 milliseconds. Or even our fast twitch is about 7 milliseconds.
So it changes from fast to slow twitch.
But even the fast twitch, we're at about 3.5 to 4 seconds here. Okay? So the action potential is about 2 to 3 milliseconds. The contraction phase is a little more than twice that for even our fastest fast twitch. So it's a slow twitch, 20 or 40 seconds to 100 milliseconds, 20 to 40 to 100 milliseconds. So we're well past the recovery of the relative refractory period by the time we start relaxation. That's why it's capable of responding to that second stimulus. Does that make sense? Now, when we were talking about neurons, do you remember my diagramming the action potential of a cardiac muscle cell? That's about 200 to 300 milliseconds. So cardiac muscle cell is not capable of this, because the cardiac muscle cell's twitch is going to look like this. Or might actually go a little bit beyond. So it's not going to, remember I talked about the importance that a cardiac muscle cell not be able to go into tetany. And that's why. Its action potential is about the same length as its twitch. Okay. Now, this is wave summation. If we continue adding muscle stimuli relatively close together, we continue to see this phenomena. This is not TREP. Okay, TREP required a cold muscle. So our reason for seeing this is different than TREP. TREP required a cold muscle, and we saw this with it coming down completely to relaxation. So that was due to changes of the myosin-titin interaction and the external collagen elastic. This is the one that is due to calcium ions inside the cell that have not completely returned. All right? So here, when we relax, remember we're pumping calcium ions back into the sarcoplasmic reticulum. And as the calcium leaves the sarcoplasm, fewer and fewer troponin molecules are bound to it, so more troponin is able to block. Tropomyosin and troponin are able to block, so when the myosin is recocked, there's no binding site available to it because the tropomyosin is already moved and being held in place by the troponin, which is free of the calcium. So we start to see relaxation. When we give the stimulus again, remember all of our voltage-gated channels have recovered. When we give the stimulus again, the same strength current passes through the entire muscle cell. The sarcoplasmic voltage-gated channels open again. All those calcium ions that would normally have come out each time come out again, not just the ones that got pumped back in. Back to our tug-of-war rope. Let's say we've got this rope. We've got 50 people on each end pulling on that rope, creating a tension. All right? Now we want to decrease that tension. So I take off 10 people from each side. We're starting to decrease the tension of the people pulling on that rope. The other 40 are still pulling. But there's not the same force because I've got 20% less on each end. Then I add another 50 people. I add those 10 back plus another 40. I'm going to have, obviously, more tension because now I have 90 people pulling on each end. Then I start to recover, start to pump back calcium ions, open up all those voltage gated channels and add another 50 again. So now I've got 100 and whatever, 80 plus 130 people. So because calcium ions remain behind, I haven't completely returned all of those calcium ions, and then I flood the cell full again. I keep getting increased calcium ions, increased troponin separating from the tropomyosin, increased myosin heads binding to the greater number of actin sites. More myosin heads means more tension. Again, it's not quite breaking the all or none rule because I've changed the ground rules. I've changed the situation. I have more calcium available. So it's not the same as starting from scratch with each stimulus, like I did with the very first diagram. So when we continue wave summation, that becomes incomplete tetanus. If my stimuli are very close together and don't allow any relaxation at all, my calcium channels remain open. They never even close. So I just continue just to allow a flood of calcium coming out. I reach a maximum state of contraction and stay there. And that is complete tetany. Oh, I started spelling a word in the middle of the word, but okay. So that would be complete tetany, which is what we see here. So the muscle just fatigues and nothing I do can get it to contract. Okay. So again, the strength of the stimulus for all of these are the same. What's changing is how much time occurs between them, and that changes how much calcium is allowed to come out or return to the sarcoplasmic reticulum. Last example is recruitment. Okay, looks a little bit like TREP. Look at the strength of the stimulus. Getting a stronger and stronger stimulus. More and more acetylcholine binding to receptors, more sodium ions entering in. Why is this not, what's going on here?
More fibers are being...
Exactly. So this is not a single muscle cell. This is not an illustration of a myofiber. This is an illustration of a muscle bundle. At the very smallest, a fascicle. And that's illustrated down here at the bottom of the screen. For my first stimulus over here is subthreshold for any muscle cell in my bundle. Nothing happens. And as I increase the strength of the stimulus, it reaches the threshold for a few myofibers. Increase the strength of the stimulus, it reaches the threshold of even more myofibers, and so on until I'm at maximum contraction. I've reached the threshold of all the muscle fibers, the myofibers in my muscle bundle. So that's recruitment. Okay. I might have 10 myofibers here contracting and 50 or 1,000 myofibers here contracting. So obviously I'm going to have a greater force from that entire muscle bundle. So back to our tug of war illustration. Let's say I have a rope attached to a car. All right, and I've got 5 people on the end of that rope pulling on the car. Then that's one muscle cell, it's one myofiber. Then I attach another rope with 5 more people. Okay? And then another rope, maybe 10 more people. All of their forces added together eventually will start to move that car. So each rope represents a mile fiber that I have added to the pulling force, increasing the overall pulling tension, if you will, of my muscle bundle. So, you're exactly right. More and more muscle cells are recruited by higher and higher stimulus strength, reaching the threshold of those cells. So that requires, you will never see this with a single muscle cell. So it looks like TREP, but TREP is the same stimulus on a cold, inactive muscle cell. All right. Talked about all of these. Okay, the next term I want to cover is, a couple of terms, is isometric and isotonic contraction. Page 32 of your lecture notes. May I erase the diagram? You guys remember what the term iso means when we talked about isotonic or isoosmotic solutions? The same as, all right? So we look at isotonic and isometric contractions. We're talking about the muscle cells involved. So here, the length of the muscle is unchanged. Tension, or the force, the generated force, increases. Other way around. Sorry. I wrote these in the reverse direction this morning. So, now there are variations of these. Sometimes the length increases, but the most common form I'm giving you is the length is decreasing. So this requires movement of an object that obviously isn't going to change in weight. So let's say that this is a 5-pound dumbbell. Okay. I am going to flex my elbow, lifting this 5 pounds. The force required doesn't change because it always stays 5 pounds. It doesn't go from 5 pounds to 1 pound or 5 pounds to 10 pounds when I do this. So it's always going to take the same amount of tension required to lift that. So the tension stays the same, but my muscle cells have to get shorter in order to decrease the distance and pull my forearm up to my arm. So the length of the muscle cell is decreasing. All right, again, there is a form. So there's another type of form where as I extend this, all right, this has to create a controlled change in length, but we're not getting to those particular types. So moving an object, you have to decrease the length of the muscle cell. That's isotonic. Right? Now, isometric is the reverse. So in this case, the length is unchanged. While the tension And you can feel this yourself. They talk about doing if you have to work at a desk or something, doing isometric exercises. They typically say to have your health checked first by a physician because doing isometric exercises can increase blood pressure. So take your hands, you can do it with your knees as well, your feet. Take your hands and push against, increasing the force that you apply that pressure. So you can apply a little pressure, you can apply a lot of pressure. Notice how the size of your muscle in your arm change. As you increase, they're going to get more firm, all right? As you change the pressure. You're not moving anything. So I'm not moving my hand from one side to the other. So the length of my muscle is not changing, but I can increase the force as I recruit more muscle cells. And I generate a greater tension within the muscle, okay? Same thing, if I try to lift up this desk with just my fingers, I'm not going to be able to lift it up, but I can try harder and harder and harder and harder, increasing the number of myofibers in my muscles that I'm trying to pull on my forearm bones to lift that. It's not moving, so these muscles, cells are not changing in length, but a greater force. I'm still exercising it, okay? So that is isometric. Now, eccentric is the other form I was talking about. You don't have to worry about that one. That's the one that if you're doing this, you have to do a controlled lowering of a weight. Muscle tone. The muscles of your back, are in a tone. They're in a state of small contraction for a long period of time. Right? We talk about if you're giving somebody range of motion and you try to move, you take their hands and you move it back and forth, or you move their fingers back and forth. There's going to be a resistance to that versus somebody who is completely paralyzed when you try to move to give them range of motion. And that slight resistance is due to tone in the opposing muscle that you're having to overcome.
Isometric, is there an exception to like if you were to use like band work for like therapy exercises where the increase or the
That's a
tension
development stretch
yeah,
of that.
Yeah, they have special machines that use like hydraulics that as you increase the range of motion, the
You're
tension
doing both.
increases too. So
Yeah.
the length would change,
So you're also
but your tension would
changing
increase at the
tension,
same time.
yeah.
So I
So,
wasn't sure if there was an exception to that.
Yeah.
It's still considered iso.
no, it would be ISO. You would be changing both. Okay. Now, the next page talks about the different forms in which energy is made available to a muscle cell. Obviously, the muscle cell uses ATP for energy, and this is shown on page 34. And the different forms, it's all ATP, all right? So what's really different is the storage form or the availability. So you've probably heard of advertisements. You can buy them at general nutrition stores and so on, buying creatine phosphate if you're going to work out. This is a storage form of ATP that makes it readily available to the muscle cell. It doesn't generate, we're not making ATP with creatine, all right, but it can bind, creatine can bind to phosphate and quickly release it. Training, working out, can increase the amount of creatine available in your muscle cells. It provides the first, if you're working out hard, it has enough ATP stored to provide energy to your cells without going through reactions, chemical reactions, for about 15 to 20 seconds. By training your muscle cells and getting them to make more creatine phosphate, you can add maybe another 10 seconds, 10 or 15 seconds, but you're not going to be able to add like 10 minutes worth of CP, okay? This is what you would use, let's say that you were playing football, and you've got the ball and you're taking off down the field. That'd be enough to last, for that run down the field. And then you would replace it through these other means. So it's a quick release form, if you will, of energy. The next quickest form is anaerobic glycolysis, where oxygen is not available. It takes place with glucose and doesn't require oxygen, as I indicated, but it's not very efficient. The amount of energy that this provides can be available in the first minute or so. Okay? I have known individuals they go and exercise and they never lose any weight. And they're doing anaerobic exercise the entire time. And yeah, it's good to increase the efficiency of your heart. All right, gets more actin and myosin fibers built in your heart, gets more capillaries, angiogenesis going on in the heart. But if you're trying to do weight loss, the aerobic type of exercise is much more efficient, if you will, more results are going to occur with that. So this is, well, we could ask you to explain it though. This is the use of oxygen. Glucose is usually the primary source, but lipids can become available if the glucose is used